We're going to take a look at solving systems of linear equations today. We're only going to cover one topic today. This tends to be something that I think students like to spend a little bit more time on just because it usually shows up on the SATs and students have a tricky or a harder time with it. They think it's a trickier topic. So when you're solving systems of linear equations, there's three possible methods that you can use. So we'll go through all three, but you're not going to be forced into any one method like you might be in like an Algebra 1 class because the SAT is multiple choice. You don't have to show your work. So just kind of keep that in mind. You can pick whichever method's easiest for the problem that you're given. So here, we're going to look at solving systems by elimination. In order to solve by elimination, you want to eliminate a variable. So you essentially want to make them have the same coefficient. So here, I can make my y terms have the same coefficient if I multiply just the top equation here by 3. So that'll give me a 9x plus 6y equals 21. And then my bottom equation, I'm going to keep the same, 2x plus 6y equals -2. So now I can eliminate my y term if I subtract this bottom equation from the top. So when I subtract, 9x minus 2x is going to give me a 7x. And then 6y minus 6y is going to cancel. And then 21 minus -2 is really 21 plus 2, so it's going to be 23. I can then divide by 7. I get x equals 23 over 7. Now, here's a little time-saving tip. If only one of your choices has 23 over 7 for x, then don't bother solving for y. You're done. Pick that choice and move on. If you have to solve for y, you're going to take this x value and plug it into either one of these two originals. I'll just plug it into the top one. So x is actually, let me put that into a parentheses, 23 over 7 plus 2y equals 7. And then I'm going to go ahead and multiply here. So when we do multiply, I end up with 69 over 7, because really this is 3 over 1, plus 2y equals 7. So now this looks pretty messy, and I can subtract the 69 over 7 to the other side and then get common denominators. But here's a little trick. If I want to get rid of all my fractions, I can multiply everything by that 7 in the denominator, and then my fractions will disappear. So here, 69 over 7 times 7 is just 69, plus 2y times 7 is going to be a 14y, and then 7 times 7 is 49. So then I can go ahead and subtract here. So that's going to give me 14y equals 49 minus 69 will be -20. And then I can divide by 14. And then I'm going to simplify. So I can take out a factor of 2. That'll give me -10 over 7. So then I've got my x coordinate. I've got my y coordinate. And some answers might just say x equals 23 over 7, y equals -10 over 7. Others might be written as an ordered pair. So just remember that x comes first, y comes second, and you'd be looking for that solution. You can also solve systems by substitution, and substitution means that you're going to substitute one variable into the other equation. So you want to figure out which variable is easiest to isolate from either of the two equations, and I think it's going to be this y here. So I'm going to go ahead and add 7x to both sides. So that bottom equation will be -y equals 20 plus 7x. And then I want y, so I'm going to divide everything by -1. So y equals -20 minus 7x. I can now substitute this in for y in the other equation, but I do want to make sure I use the other equation, not the one that I used to solve for y. So 2x minus 3, instead of y, it's a -20 minus 7x, that's what we solved for, equals 14. And then we're going to distribute this -3. So that'll be 2x plus 60 plus 21x equals 14. And then we can go ahead and combine our like terms here. 2x and 21x will be 23x plus 60 equals 14. And then I can subtract 60 from both sides. And that will give me a -46. Divide by 23, and I get x equals -2. Again, if that's or if there's only one choice that has x equals -2, stop and move on to the next question. If you need to solve for y, we can take this x and plug it into one of the originals. Or again, a little time saving tip, y is already isolated here. So if we plug it in there, it's just a little quicker. We have y equals -20 minus 7 times -2. So that's -20 plus 14, which is going to give us y equals -6. So again, if it's not written this way, you might be looking for the ordered pair -2, -6. You can also solve systems by graphing, but I would only recommend to do this if the graphs are already given, because if you don't make your graphs perfect, then you're not going to find the right solution. And so when you're solving by graphing, you're just looking for where those graphs intersect. So you're looking at that point of intersection. There are some special cases. So we have kind of no solutions and infinitely many solutions, and we'll talk about that in just a minute. But systems with one solution are going to intersect at exactly one point. That means that we're able to solve for x and we're able to solve for y. So here, we're looking at this set of equations, and we want to find a value of a so that we have one solution. If we need to be able to solve for x and y, we can't find ourselves in a scenario where both variables are going to disappear. So like if we were going to use elimination in this system, I could multiply that top equation by 2. It would become 14x plus 4ay equals 8. And then my bottom equation is 14x plus 4ay equals 8. So if I go to use elimination, I then subtract these and they disappear. I'm going to get a 0 over here. Essentially, I need a case where these y's aren't going to cancel each other out. I added an a here. This is just 4y on the bottom from recopying this equation. So these would cancel. These would cancel. I need these to not cancel. I need a y left in my equation. So essentially, a can be anything as long as 4ay does not equal 4y. So if we divided both sides here by 4y, we just can't have an a value equal to 1. Because if a were equal to 1, then we end up with a scenario where it's 0 equals 0. Which if it's a true statement means that we have infinitely many solutions. So you would be able to report any value other than 1. So here, like I said, infinitely many solutions, if they're graphed, the lines are identical, so they would fall right on top of each other and your graph would look just like one line. And so that's technically called a linear pair, so the x and y coefficients would match or could match by multiplying one of the equations by a constant. So when solving by elimination, like I said, that result is 0 equals 0, so a true statement. So here's an example here to design a system with infinitely many solutions. So I'm just going to pick an equation. I'm going to say 2x plus 3y equals 4. So a linear pair would be any multiple of this equation. So if I multiplied this equation by 3, I would have 6x plus 9y equals 12. This is a linear pair because if I were to then go back and multiply this by 3, I'd have the same equation. So when I solve by elimination, I would end up with 0 equals 0. Systems with no solution are going to be graphed as parallel lines, so they never cross. They wouldn't have that intersection point that systems with one solution have. So when solving a system by elimination, you end up with an untrue statement if you have no solution. So it's similar to just equations and inequalities in general. If the statement is true, that tells you that you have infinitely many solutions or all real numbers. And if the statement is false, that tells you that you have no solution. So if you did elimination and you ended up with 7 equals 4, that's not a true statement. So that would tell us that system has no solution. So here's an example. They're asking us for a scenario where we have no solution. So essentially, you want both your variables to disappear and you want a false statement. So say we looked at trying to make those x terms match. Maybe we multiplied this first equation by 2 and the bottom equation by 9. Then we have an 18x minus 28y equals -6. And on the bottom, we have an 18x minus 9ay equals negative 36. And so essentially, if we were going to subtract these, we want all of our variables to disappear if we have no solution. And so these are going to disappear. We need these to disappear. So essentially, we need the negative 28y to be the same as the negative 9ay. So if we go to solve here, we can divide both sides by y, and those will disappear. We have negative 28 equals negative 9a, and we can divide both sides by negative 9. So we end up with 28 over 9 when we simplify those negatives. So for your assignment, you have the solving systems of linear equations on Khan Academy. Remember, 3 out of 5 or more will get you full credit for the assignment.